That leads us to plate tectonics. So now we have a evidence, we have a mechanism, and we have evidence of that mechanism. Now we have plate tectonics. So in the 70s, around the time that map was being produced of the sea floor, textbooks were rewritten to incorporate plate tectonics into our knowledge base of geology. Here it is. The plates, the earth is broken into plates. So on this map, they're labeled, we live on the North American plate. I'll put ourselves here. To the south of us is a Caribbean plate. To our east, we would have to cross the ocean basin and get to the mid-ocean ridge before we were onto another plate, the African plate. To the west, we would need to go all the way to the coastline and pass over the San Andreas Fault and be on the Pacific plate. The lithosphere is what's broken to be so the solid rigid lithosphere is making up the plates. And this is now the unifying theory of geology. It's what we go back to when we talk about the basics of geology. On this map, the boundaries, the plate boundaries, where one plate touches another, they have three different kinds on here. The ones with we call these teeth, those little triangles, that marks a convergent plate boundary where plates are coming together. The plates that are that have the arrows going in opposite directions, those are transform boundaries, where one plate is sliding in the opposite direction of the other. And the third kind of plate boundary are the other ones that are just line segments, and those are the divergent plate boundaries where plates are moving apart. You can see along the Mid-Atlantic Ridge. These arrows are showing the plates moving apart. Okay, so here is a big table, it's a lot of words, but it summarizes, I'm going to turn off. It goes through, the table has the three, this is from your textbook, the three different kinds of plate boundaries. Divergent, and there's two kinds. Convergent, and there's three kinds. Transform, and there's two kinds. And the kinds all have to do with the nature of the continent, the crust. Is the crust continental or is the crust oceanic? So for divergent, you can imagine that the mid-ocean ridges on either side is oceanic crust. For the continents, like the East African Rift Valley, the Red Sea, the Gulf of Aden, the Gulf of California, down there below California, Mexico, that is continental crust that is pulling apart. The convergent plate boundaries, where at the boundary plates are moving together, you can have two pieces of oceanic crust moving together, or lithosphere. You can have oceanic crust and continental crust coming together, and you can have continent-continent collision, where mountains are being built and coming together. And then transform boundaries, those can be in oceanic crust or in continental crust. So from that, there are different processes that are going to happen depending on the nature of the kind of the crust. There are different features going to be at those boundaries. Are there earthquakes? Yes, to all of them. Are there volcanoes? There are places where the answer is yes and places where it's no. The no's would be at transform plate boundaries. There's no mechanism to have a melt. And there's a no at continent-continent collision, another one where there's no real mechanism for melt. And then the last column here has examples from around the world. All right, let's look at cartoons of each of the kinds of plate boundaries. This first plate boundary, a divergent plate boundary, plates are pulling apart, and for the most part, we have mid-ocean ridges. There are some places on continents where it's pulling apart, and we have a continental rift. A convergent plate boundary, like in B, the most prominent kind, is where Oceanic crust, it's heavy and dense, goes underneath continental crust. As that oceanic crust goes down, there's water in there that produces a melt as it gets hot, and then it rises up to form a chain of volcanoes within the continental crust. A transform plate boundary, you just have offset between the two segments. There certainly are earthquakes, but there is no volcanism. All right, you can also have divergent plate boundaries in continental crust. So here is an example. I'll turn my face back on. Here is an example of rifting. This is called a triple junction. 1 for the Red Sea, 2 for the Gulf of Aden, and 3 for the East African Rift. At that place, the continental crust is splitting apart in 3 segments, all coming together at one point to make a triple junction. I can't really do that with my fingers. Along the East African Rift Valley, there are very deep lakes, some of the deepest lakes in the world, Lake Victoria, Lake Turkana, and there is also like Mount Kilimanjaro, a giant volcano. In the Gulf of Aden and the Red Sea, there is basalt forming at the bottom of those ocean basins. So step 1, you would have upwarping, you're just a deformation of the continental crust as magma rises into underneath it. You would form a rift valley that would obviously, because it's a low point, fill in with water, eventually get a linear sea like the Red Sea or the Gulf of Aden, and if it progresses, you get a whole ocean basin like the Atlantic. Iceland sits right on the Mid-Atlantic Ridge. So if this is the Mid-Atlantic Ridge going right through the country of Iceland. One of my bucket list things to do in my life is to scuba dive along that Mid-Atlantic Ridge. Transform boundaries are like those in California. That's kind of the biggest one in the world. This is the San Andreas Fault System that cuts through from Southern California to Northern California. The very tippy Northern California up here, that segment is a subduction zone with the Juan de Fuca plate. Zooming in on, this is the Carrizo Plain. There's offsetting of these creek beds here. So that one is within continental crust. Other transform boundaries, we can find hundreds of them offsetting the mid-ocean ridge. So look at this diagram. The axis of the ridge kind of goes left to right across this diagram. The arrows show the pulling apart of the ocean basin at the divergent plate boundary. And cutting through the middle of it is what's called a fracture zone. And along that fracture zone is transform motion, and that's just a tiny little transform boundary. All right, convergent plate boundaries. The plates are coming together, and there's 3 kinds, just like that big table had. Ocean-ocean convergence, ocean-continent convergence, and continent-continent convergence. For the first 2, you've got oceanic crust that's going underneath either younger, more buoyant oceanic crust or less dense, more buoyant continental crust. In either case, you have subduction, old oceanic crust is going down, and that's going to generate earthquakes and volcanoes. In continent-continent collision, 2 buoyant pieces of continent, neither of them are going to subduct, they're just going to ram into each other, and you're going to have earthquakes. Let's look at that. Here is an ocean-ocean convergence. So on the right is older oceanic crust. It's going underneath this younger oceanic crust on the left. When that happens, this fan-looking thing here is called an accretionary wedge. It's not labeled here, but these sediments are in an accretioning wedge. It's wedge-shaped, as the ocean sediments are getting scraped off. That old oceanic crust is going to dive down into the asthenosphere. It's bringing water with it. It's going to melt, and they're going to get a chain of volcanoes called a volcanic island arc. At a convergent plate boundary with ocean and continent, same thing. You have the old oceanic crust going down, the accretionary wedge of sediments. The melting is different. It's going to melt and pick up and assimilate and melt a little bit of this continental crust. So the nature of the volcanoes are a little different, but you have a mountain belt with volcanoes along that continent. Lastly, the continent-continent convergence, where it's just two pieces of continent coming up together and pushing and pushing and pushing. Eventually, there's going to be some give because the plates are going to keep moving. And you get really large faults within that. So lots of faulting occurs within that mountain belt. Oh, you get big tall mountains like the Himalayan mountains. Okay, so what makes the plates move? I talked a little bit about that heat that occurs that's in the earth. The hot rocks are going to rise as their density decreases, and then they get cold, and then they go back down into the asthenosphere. That is called adiabatic convection. These days, there's newer ideas, not super new anymore, but there's this idea of ridge push, where the actual ridge is going to have some topography to it because there's been volcanoes there, and that weight of that is going to push the plates apart. So hold your hands like this and pull them apart. They're going to have some push to it. Then on the other side of the ocean basin, there's a slab. There's that cold, dense, heavy oceanic crust. It's huge, right? Like the whole ocean starts going into that subduction zone, and gravity is just going to pull it down in there once it starts. So ridge push and slab pull is a kind of newer idea for what drives plate tectonics. All right, the plates move at different rates. This is a map showing the spreading rates. So slower rates would be in the purples, and then quicker rates, higher velocity. Over here on the Nazca and Coast plates, we've got faster spreading than, say, the mid-Atlantic ridge. But in general, we're looking at 1 to 20 centimeters per year. The variability, but in general, it's a little bit smaller window, 2 to 10. I'd say average 3. The plates also are moving in different directions. These arrows on there show the direction, and the length of the arrow also is showing the velocity. So velocity is pointed, the velocity and the direction are done here with those red arrows. Notice over here in North America, South America, there's a bit of rotation to the plates and fast moving plates elsewhere. Okay, hotspots. These are not at a plate boundary, like the top says there. What they are, dotted around the world, are volcanoes that are not at plate boundaries, and they are active, and it occurs when there's what's called a mantle plume, where within the mantle there's a hot spot that burns up through oceanic or continental crust. So for the United States, our two most famous ones would be Yellowstone and also Hawaii. And they just burn a hole in the crust and create a chain of volcanoes. Hawaii is a really good example. The Hawaiian Islands look like this, the volcanoes do. They are made up of basaltic lava flows that have a really low viscosity, a low resistance to flow. In the volcano, the lava flows a really long ways, so you get these huge domes of volcanoes. On the big island of Hawaii, Kilauea and Mauna Loa are active. The current position of the hotspot is down here right off of the island, so that will eventually make a new island that we could live on. Away from the hotspot, the islands and rocks of Hawaii get progressively older. So right at the hotspot, the rocks are 0 years old, up to 1 million, and then further away, they get to be 4 and 5 million years old. So the shows the movement of the Pacific plate across that hotspot that stays in place.